Hi, everyone. Today we're going to talk about functions. And let me start with the definition. If x and y are sets, then we say that a function, also called a map or mapping, from x to y, we denote it by f, x, arrow to y, or we can also write f over the arrow. So this function is defined as a subset inside x cross y. Sometimes we can also write it as gamma of f, where gamma denotes by stands for the graph of a function. And in this subset, each element x appears as the first component of exactly one ordered pair x comma y in gamma of f. Informally, I can say that a function is a rule that assigns to each x in the set capital X exactly one y in the set capital Y. This y is then written as f of x. And when x goes to f of x, we can write it like this. X in x maps to f of x inside y. And when we denote this rule on the elements, we add this vertical line here. The two related definitions to functions are domain and codomain of a function. The domain of f is x. So this is where the function starts. And the codomain is y. Inside of y, we can define the image of f. And it is the subset that is denoted by im of f. It consists of every f of x where x varies over all elements of the set x capital. And one can draw a picture to relate all these notions. So this will be X. It is the domain. And let's say that this is Y, this is the codomain. Then F sends some elements, sends all elements of X to some elements in Y. And every element that has some element mapping to it forms a subset called image. So this will be image of F. We say that F is injective if for every pair of elements x prime, if they get sent to the same element in Y, then it means that they were the same element to begin with. In other words, no two elements go to the same element. And the dual notion is surjectivity. So F is surjective. If for every element in the codomain, there exists a pre-image in X. So there exists X such that F of X is equal to Y. And we can notice that surjectivity is equivalent to the situation where the image of F is equal to the whole set Y. So now I have talked about what a function is. I talked about domains, codomains, and images, and injectivity and surjectivity. Now let me give you some examples. So the first one is the example of something that's not a function. Let's say that X and Y are both finite sets for simplicity. So X is the set of 1, 2, 3. Y is the set of 4, 5, 6. And I can define a subset of X cross Y which consists of pairs 1, 4, 1, 5, 2, 6, and 3, 6. You can see that 1 appears in 2 pairs, which contradicts the first, which contradicts this assertion. Now, let me consider another subset S2, a smaller one, 1, 4, and 2, 6. Now you can see that these numbers 1 and 2 appear in exactly one ordered pair each, but 3 does not appear in any ordered pair, which contradicts this requirement. Not functions. Now let's consider some functions from z to z. So x equal to y equal to the set of integer numbers. Then I can consider the simplest example where f is the constant function. F of x is equal to 0 for all x. And this is called a constant function or a constant map. You can see that it is neither injective nor surjective. And this is because f of 0 is equal to f of 1 is equal to 0. So the element 0 has two preimages, which proves that it is not injective. And on the other hand, there does not exist x such that f of x is equal to 1. So there is an element which doesn't have a preimage. So it is not surjective. And in the second sense, we can also determine the image of this function. It is the subset of one element. And we know that this is definitely not the set of integer numbers. Now, I can talk about polynomial functions where I send x to x cubed. I claim that it is injective because if we have that f of x is equal to f of y, then x cubed is equal to y cubed. And you can check that this implies that x is in fact equal to y. However, it is not surjective because only the numbers that are powers that are third powers of another integer number can appear in the image. And for example, 2 is not one of them. So there is no integer number that would give us 2. So third cubed root of 2 is not an integer. And now let us consider this example where I send x to minus x plus 1. You can check that it is injective. And at the same time, it is also surjective, because we can solve minus x plus 1 is equal to y for each y in the codomain. And write it as minus y plus 1. So we see that this function is both injective and surjective. And when a function satisfies both of these properties, it has a special name. In this case, we say that f is bijective or a bijection. It is a bijection if it is both injective and surjective. Now that we have defined functions from x to y, we can organize them into sets. And I denote the set of all functions from x to y by writing hom from x to y. And if we are given another set z, we can also write the set of functions from y to z. It turns out that we can define composition of these functions. And the composition can be written itself as a function from the direct product of hom from y to z with hom from x to y. And its codomain is the set of maps from x to z. It is defined by sending an ordered pair f comma g to something that is denoted by f circle with g. So this is the notation. And we can write it on elements as fg of x is f of g of x. Sometimes we also write f circle g as fg for brevity. Let us consider an example. If all of the three sets are the set of real numbers, then I can compose f that sends x to x plus 1 and g that sends x to 2x. And what I will get is the following. So fg evaluated at x will be f of g of x. It will be f of 2x. And then we shift 2x by 1. And because all of these sets are the same, so we really care about this y in the product being the same. But here, every set x, y, and z is equal to r. So this red requirement is satisfied. So we can compose it in the other direction, and g of f of x will be g of f of x. F of x is equal to x plus 1, and g of x plus 1 is equal to twice this quantity, 2x plus 2. I have a small terminological remark. The notation hom comes from the word homomorphism. And homomorphism is a certain class of maps that also satisfies some properties. It should preserve certain algebraic structures. And we will see it later. We will see this word later in the course. There is a nice exercise for understanding of composition, which says that composition is associative. Namely, you should prove that if we have three functions, f from x to y, g from y to z, and h from z to s, then their composition is defined regardless of the order in which you calculated. So hg composed with f is the same as h composed with gf. And in order to verify this equality, you will have to plug in elements of x and evaluate both sides on x. So for example, you have hg of f of x will be equal to hg of f of x, and so on. For any set x, there is a distinguished function called the identity function. Yeah, and it is denoted by ID subscript x. It is defined on elements trivially. So it sends each element x to itself. And you can also do the following exercise. First, you can show that for any function f from x to y, composition with the identity on any side is does not change f. So identity of y composed with f is equal to f, as well as f composed with identity of x is equal to f. Furthermore, you can prove that if you fix a function f from x to y, then it is a bijection if and only if there exists a function g in the opposite direction, y to x, such that the composition in both directions is equal to identities. So f composed with g is equal to the identity of y, and g composed with f is equal to the identity of x.